I'm Harish Kumar of CSC, Bearing Road number 8. Today I'm here to present you about a major project, detection of ships in States. Detection of ships in seas and oceans plays a crucial role in maritime security and protection. In existing ship detection systems like AIS, Automatic Identification System, AMS, Vessel Monitoring System, NRIT, long-range identification and tracking, using sensors and transporter system detections. It usually works by installing an AIS device on the ship which continuously exchanges data with other vessels and maritime authorities. However, these systems have some problems in using it, which reduces its efficiency, and these are prone to some software threats, which keeps a major thing to get a new system to existence. Every year, about 25 ships sink or go missing, causing great human and economic loss. Monitoring of ships through our automatic identification system (AIS) have been some shortcomings like poor concealment, limited range, and installation of maintenance of sensors with the TDCs. A more effective and computationally fast method is required which should satisfy the constraints to compute the huge data in terms of images, predict the ship accurately from the complicated backgrounds or complex backgrounds, to detect ships that differ in shapes and appearances effectively. Coming to the solution, we propose the method which uses the abundant satellite imagery along with the edge-cutting technologies like deep learning for detection of ships selected. We will be using Keras along with TensorFlow to build a neural network which could successfully predict ships on satellite images. Remote sensing. Remote sensing is the science of obtaining the information about the objects or areas from a distance, typically from aircrafts and satellites. Remote sensing has a major applications in monitoring oceans and coastal activities. Remote sensing data has crucial applications in maritime activities. Dataset. Dataset named ShipNet dataset taken from the CADL website. It consists of satellite images extracted from planet satellite imagery collected over San Francisco Bay, California, US, and it also contains the resident coastal areas of the California cities. All the images are of size 80 into 80 height and 80 width, are colored images with two classes, ship class and non-ship classes. Convolution neural network. In deep learning, convolution neural networks play a vital role in image recognition and processing, especially designed to process the pixel data. A neural network depicts the same like a human brain function which recognizes the objects same like how neurons work in the brain. Convolution neural networks takes the input through a series of layers which ideally compute the output and ideally compute the input to an effective output. A fully connected neural network. The input of the neural network is a image, especially in our project, it's a 2D image. It's basically a 2D array fed to the network. It is fed as a one-dimensional array to the network. And a fully connected network is more generous, structurally agnostic, and it is also called as universal approximators. CNN for classification. Classification or detection of ships is done using a layer structure of the CNN, and these layers consist of a convolution, a non-linearity, and a pooling layer. We will see each one in the next slides. Convolution. Convolution is generally a mixing of two information according to the specific rules. Mathematically, it uses addition, multiplication, and integration of two components. Here, we mix input image with the kernel and produce output. The kernel slides all over the image and produce an output, and this sliding is called a rectangular sliding. It's often regarded and the output of these gives us a future map. An image with 80 into 80 size with 3 into 3 kernel size takes the 80 into images into 3 into 3 image patches and compute with the kernel, which produces one feature of one pixel of the feature map. We can visualize this in this slide. Coming to nonlinearity, deep neural networks uses nonlinearity so that the same output is not generated using a linear function which would compute two inputs into the same output. In this, we are using the ReLU function, rectified linear UML, which ultimately converts all the data values to zero, giving us a no output to the next phase. Cooling is applied after every convolution layer, which prevents overlapping of filters to produce the same features. Convolution in the systems goes like at every convolution layer, minimum of a set of features are extracted. Right? In the first one, the lower end features are extracted. In the second network, second convolution, some medium level features are extracted. The same way, the third convolution, high end features are extracted. Using this without cooling, there will be an overlapping of the kernels, and it's hard to detect the different types of filters in the code. So, max cooling reduces the dimensionality, and it's also contribute for the spatial invariance, making us available to restrain all the features of the image or object. Convolution development. A convolution neural network, a final view of a project can be visualized here, in which at every convolution from the input, we will be obtaining the features and setting it out with feature maps, and with max cooling, we will be forwarding that to extract more features and more advanced features. Likely, after the end of the first phase, we will be transferring the output of these all layers to the softmax layer, which ultimately gives us the final output. Coming to the process flow of the project, initially it starts with loading the shipment data set that it should solve data preprocessing and normalization. We will be getting the data in the pixel format, which needs some preprocessing techniques, so that it helps in working of the model ideal. Normalization, we will be dividing all the pixel values with 255, so that we will be getting the pixel range, which is generally from 0 to 255 to 0 to 1. After preprocessing is done, then we will be splitting our data into our training set and testing set. After training test and testing set are made, we will be training our model with training set. When training of the model is completed, a satellite image from the user, we will say it as an input image, is taken from the user, and as the input image is not in the pixel format, we need to rasterize it so that we should convert it into the pixel format. After preprocessing of the input image is done, then we will be splitting our input image into 80 into 80 patches, and each 80 into 80 patch is sent to the model to make the predictions whether it contains the ship or not. Any patch on the image contains the ship. Those coordinates along with the result, ship or not ship result, is stored in our arrays so that we can predict the final output with that. Storing the predictions in our containers, and finally we will be displaying our output image with the bounding boxes on the image where the ships are available. We can see our sample training images. Training image consists of both ship and non-ship images. We can visualize here, and a sample test image, we say the user test image is here. Is this is a satellite image taken the satellite at San Francisco Bay, California, US. To summarize the project in one slide, initially we will be training a data set with a neural network. After the training is done for the network, then we will be taking our input image, dividing the input image into patches, and each patch of 18 to 80 size is, is, is sent to the neural network for predictions and predicted image, and all the predictions are done. Then we will be displaying our output image as you can see on the right. The bounding boxes on the detector ships. To conclude our project, we have successfully made a project which could detect ships or extract ships from satellite images. Our model was 95% accurate, has achieved 95% accuracy, and using more complex systems and like more higher end versions of GPUs like GTPs, Titan X, will be will improve its potential in real time processing. We can get a more accurate and more faster results in real time. Future scope. Using pre-trained models like YOLO, SSD mobile net, and exception models, we can even classify the ships into different categories in satellite images. Like there will be many ships like container ships, tourism ships, etc. We can classify those images itself in satellite images. Same model can be implemented to detect the forest fires in satellite images. As we can see, forest fires in California is captured by the satellite. The feature enhancement of this project is under research. They are using generic addition network, which is currently under research. Thank you.